Okay, let's talk about our limits and continuity test review. Here in question number 1, it says that f of x is equal to 3x minus 4, and they want us to find the limit as x approaches 0 of f of x minus f of 0 over x. Now remember, whenever we have a limit where the variable is approaching a number, first thing we should always do is try to plug in that number. So I'm going to plug in 0, and I get f of 0 minus f of 0 over 0, which of course is equal to 0 over 0. So that indicates that there probably is a limit, and we need to do something else to figure out what it is. So I'm going to go back to our original statement. The limit as x approaches 0. But instead of writing f of x again, I'm going to go ahead and substitute in what f of x is. F of x is equal to 3x minus 4. So I'm going to sub in 3x minus 4. And then we have minus f of 0. And if I look at f of x and plug in a 0 there, let me just do this off here to the side. F of 0 would be equal to 3 times 0 minus 4, which is negative 4. So I'll plug in negative 4 for f of 0. And then this is still over x. So now since I have minus negative 4, that becomes plus 4. And so I have negative 4 plus 4, and those would cancel each other out. Negative 4 plus 4 is 0. So those cancel out. And I'm left with the limit as x goes to 0 of 3x over x. Well, now I have an x in the numerator and the denominator. Those can cancel out. And it looks like my limit is 3. Let's move on to question number 2. In this question, we've got some trig functions. Theta is our variable this time, and it's approaching 0. So the first thing we should always try to do is plug it in. 1 minus cosine 0 over 2 times sine 0 squared. I'm going to rewrite that using that kind of notation, which generally makes a little more sense to students. So let's evaluate this. Cosine of 0 is 1, and 1 minus 1 would be 0. And then sine of 0 is 0, and 0 squared would be 0 times 2 is still 0. So I have 0 over 0. Don't have an answer yet, but it seems like a limit does exist. So we need to do some manipulation here. So I have 1 minus cosine theta in the numerator. There's really nothing I can do with that. So I'm going to leave 1 minus cosine theta. But in the denominator, I have this sine squared. Now if you think about our Pythagorean identity, I'm just going to write this here and then I'll erase it. We have an identity that says sine squared plus cosine squared is equal to 1. And if I solve that identity for sine squared, then I get 1 minus cosine squared. That's equal to sine squared. And so that's something that I could replace sine squared with here in my limit expression. So I'm going to make this 2 times, and instead of sine squared, I'm going to put 1 minus cosine squared. Now if I plugged in 0 now, I would still get 0 on the top and 0 on the bottom. And so I haven't really done enough manipulation yet to get a limit. We need to do some factoring. I still can't do anything in the numerator, but here in the denominator, I have 1 minus cosine squared, which can factor to 1 plus cosine, 1 minus cosine. That's a difference of 2 squares, 1 minus cosine squared. And so we can factor it like this. Now I have 1 minus cosine theta in the numerator and the denominator. So limit as theta approaches 0 of 1 over 2 times 1 plus cosine theta. Now I have a simplified version, and I want to plug in again and see if I get an answer this time. So I'm going to plug that 0 in for theta, and cosine 0 is equal to 1, and 1 plus 1 is 2, and 2 times 2 is 4, and so that limit is equal to 1/4. Next question. On this question, we're being asked to evaluate a limit as n goes to infinity. Now this is a little bit different. If n's going to a number, we want to plug the number in. But if n's going to infinity, this is where we need to think about which part of my rational expression is bigger. Is this bigger on top or bigger on bottom? On top, I have a natural log function, and on the bottom, I have a parabola, a quadratic. The quadratic function, as n goes to infinity, is going to be much bigger than a natural log function. And so since my expression will be bigger on bottom as n goes to infinity, then that means that my limit here is 0. Bigger on bottom, the limit is equal to 0. All right, on question number 4, we have this graph, and it just says to discuss the one-sided limits and the limits at points A, B, and C. So I'm just going to write a few statements here that would be true about this graph. Limit as x approaches A. If I'm looking at all of A, B, and C, at A, this is the only place where the limit actually exists. And I don't have to write exists because I can say the limit as x approaches A is equal to 1. You can see that as I approach A from the left and from the right, that the function on both sides is approaching the value of 1. So a limit does exist at x equals A, and that limit is equal to 1. Now I could say also about A that the value of the function at A is equal to 2, which is not equal to the limit as x approaches A. And that's how we end up with a hole up there in the graph. Our function is not continuous at A because there is a hole. At B, we can talk about one-sided limits as B. The limit as x approaches B from the left. If I look at the graph and I'm approaching B from the left, my function is going to, whoops, sorry, I was trying to move the screen over, is going to positive infinity. And if I approach B from the right, on that side, the function is going to negative infinity. And finally at C, the limit as x approaches C from the left. If I'm approaching C from the left, the function is coming up, it's approaching 0. And the limit as x approaches C from the right of f of x. If I'm approaching C from the right, my function is up here approaching 1. So you can see here at B and at C, the limit does not exist at those 2 points because for B, my one-sided limits are going to infinity, and that's not a limit. And then at C, my one-sided limits are equal to 2 different values. So I do not have a limit there. All right, question number 5. Which of the following functions are continuous at x equals 0? Being able to answer this question requires that you know what your parent function graphs look like. For natural log x, if you remember, that graph looks like this. And it's not even defined at 0, and so there's no way it can be continuous at 0. 0 is a asymptote. So this one is a no. So now let's move on to e to the x. The e to the x graph looks like this. This function is defined at 0 right there, and it is continuous at 0. We don't have a hole, a break, or anything, so this would be a yes. Now the tangent graph, this may be a graph that maybe we don't remember this one as well. If you do remember the graph, it looks like it does have asymptotes, but the asymptotes happen at pi over 2 and negative pi over 2. The graph looks like this, and so you can see we are continuous at 0. If you didn't remember the graph, though, you could think about the fact that tangent is equal to sine over cosine. And if I plug in 0 to that expression, sine of 0 is 0, and cosine of 0 is 1. And so 0 over 1, that is a value. It's equal to 0. So tangent is defined at 0, and therefore it is continuous. So tangent is a yes. Our last one is 1 over x. That's the rational function. The graph looks like this and is not defined at 0. 0 is an asymptote. And actually we could plug 0 into the function 1 over 0 and realize that it's undefined. So this is a no. All right, let's go to the next question. If f of x is continuous for all real numbers and f of x equals this rational expression when x does not equal 3, then what does f of 3 have to be equal to? So notice this is saying we want f of x to be continuous. Obviously, if x is equal to 3, we're going to be dividing by 0, and it would not be continuous there. So we need to find the value to assign to f of 3 to make the function continuous. So the first thing we should probably try is to plug in the 3. If I do that, I get 3 squared times, or minus 7 times 3 plus 12 over 3 minus 3. And on the top, that gives me 0, and on the bottom, also 0. So I have 0 over 0, not an answer, but it tells me there is a limit, and so I need to factor. So let's factor the numerator. My denominator can't be factored. I'm going to go ahead and write it down. In the numerator, I'm going to have x and x, 4 and 3, and both of them are negative. Now I can factor out, I can cancel out x minus 3 from the top and the bottom, and I'm left with x minus 4. And so now what I want to do is plug that 3 in for x. 3 minus 4 would be equal to negative 1. And so that means that I want the function to be equal to, I want f of 3 to equal negative 1. And that would be my answer. That would make the function continuous. On question number 7, here we have a piecewise function. And it asks us to determine when this function is not continuous. We want to find those places where it's not continuous. If I look at the pieces, I have a linear function, a parabola, and cosine, and all of those graphs are going to be continuous. So my only possibilities for discontinuity is when I'm switching from one function to the next. And so notice that the first function, 3x plus 3, the domain for that piece is x all the way up to negative 2. And it includes negative 2, but then I switch to the parabolic function, the x squared plus 1, that domain starts at negative 2. So what I want to do to find out if it's continuous is I want to know if those two pieces are connected, if they're equal to each other, whenever x is negative 2. So I'm going to plug in negative 2 to the first function, and I get negative 3. And then if I plug in negative 2 to the second piece, I get 5. These two numbers are not the same, they're not equal, and therefore f of x is not continuous at x equals 2. Not continuous at x equals, not 2, negative 2. Because my two pieces are not meeting up at the same point. Now we're not finished, we've got to check out the 0 as well. Notice that x squared plus 1, that domain goes up to 0, and then we switch over to the cosine function. So I'm going to plug 0 in to x squared plus 1. 0 squared plus 1 is equal to 1. And then I'm going to plug 0 into the cosine function, and cosine of 0 is also 1. So those two values are the same, and therefore those two pieces are meeting up, and so the graph is continuous at 0. And so our only place for discontinuity is at x equals negative 2. All right, question number 8. Here they tell us if the limit as x approaches 3 of f of x is equal to 7, then which of the following must be true? Now this is important. Some of these statements that follow, they could be true, but they don't have to be true because the limit exists. So let's think about the different statements that are here. F is continuous at x equals 3. Well, right now all that I know is that a limit exists. But the limit, remember, could be a hole. Even if your graph looks like this, a limit still exists, but there could be a hole. And so that means that f does not have to be continuous at x equals 3. It might be, but it doesn't have to be. So we're going to say that one's false. The next statement says that f of 3 equals 7. Now again, I can go back to the picture that I just drew. We might have a hole there at 3, 7. When x is 3, the limit is 7, but we don't know that the value of the function is 7 because it might be a hole. And so that one too is false. Now these next two statements, the limit as x approaches 3 from the left equals 7, the limit as x approaches 3 from the right equals 7, those two statements are true. In fact, when you know that a limit exists, these two things are the only two things that you know. Question number 9. If a does not equal 0, then the limit as x approaches a of x squared minus a squared over x to the fourth minus a to the fourth is ... Well, this one seems a little weird because we have x approaching a, but a is representing a number here, a constant, and so whenever x is approaching a number and a limit, the first thing we should do is plug it in. So I'm going to plug in a squared minus a squared over a to the fourth minus a to the fourth. And if I do that, I get 0 over 0. So it seems like we probably have a limit. We need to do some factoring to find out. So limit as x approaches a. So in the numerator, I have x squared minus a squared. And that's a difference of two squares, which factors to be x plus a, x minus a. Now in the denominator, I have x to the fourth minus a to the fourth. And since those exponents are even, that's also a difference of two squares. So when I factor this, instead of x plus a, x minus a, we're going to have x squared plus a squared times x squared minus a squared. Just like we would factor a difference of two squares, except that our exponents were 4s instead of squares. So at this point, I don't have anything that's matching exactly to cancel out, but notice here I have x squared minus a squared, and that could be factored even more. And so I'm going to factor it just here below. X squared minus a squared is equal to x plus a, x minus a. So now I've factored that factor. Now I have factors that can cancel out. I have x plus a on the top and the bottom. I have x minus a on the top and the bottom. So now I've canceled stuff out. And I'm left with the limit as x approaches a of 1. Whenever everything in the numerator cancels out, you need to put a 1 there. We've got to have some numerator. And then in the denominator, I just have left x squared plus a squared. And so now, last thing I should do is plug in again. And if I plug in a again, I get 1 over a squared plus a squared, which is 1 over 2a squared. And that is your limit. Okay, on this question, number 10, given the graph below, which of these statements is true? So let's look at each one. First statement says f of a exists, and I'm just going to stop there and check that. F of a exists. If I look at the graph, here's a, and notice I've got this colored in circle right here, so that is true. F of a, that part of that statement is true. F of a exists. But the limit as x approaches a does not exist. Well, if I go back to a, you can see here that we have jump discontinuity. My limit from the left this way is approaching a different value than my limit from the right. And so therefore the limit does not exist And that whole statement is true. So I'm going to put a true next to that one. Next statement says the limit as x approaches b of f of x exists. Well, at b, you can see that we've got an asymptote. On both sides of it, we are going to positive infinity. But even though both sides are headed towards the same value, infinity is really not a value. And so whenever we're headed to infinity, the limit does not exist. And so this is false. There is no limit at x equals b. And the last statement, f of x is continuous at c. Well, if I look over here at c, I can see that we have a hole. So a limit exists at c, but the function is not continuous because we do have a hole. And so that last statement is false. Question number 11. So this is where we get into, these last two questions are going to be free response type questions on your test. And I'm going to give you an expression similar to what we have here. Limit as x approaches negative 2 of x squared minus 4 over x plus 2. And what I want is for you to show me that limit numerically, graphically, and algebraically. Now for this first one, I think I would start with algebraically first. And the first thing I'm going to do, which we should always do if x is approaching a number, is we're going to plug it in. So I get negative 2 squared minus 4 over negative 2 plus 2. And that gives me 0 over 0. So I probably have a limit, but I need to find out what it is. So I'm going to factor my numerator, and I get x plus 2, x minus 2. My x plus 2's cancel out. And I'm left with the limit as x approaches negative 2 of x minus 2. And so finally, my last step, I should plug in again. And negative 2 minus 2 equals negative 4. So I found the limit algebraically, and it's equal to negative 4. Now let's look at how you would show me that limit graphically. I am going to let you use a calculator on this question, and so you could type in the original function and get the graph, but what I want to make sure that you think about is that at x equal to negative 2, there should be a hole on the graph, and you're not going to be able to see that on your calculator, but we can see it algebraically right here because when let me get a different color, we can see it right here because when I plug in negative 2 plus 2, I get 0 in the denominator, and that means my function should be undefined at negative 2. So I'm going to mark negative 2. Now I've already figured out algebraically that my limit is at negative 4. So I'm going to put that here, and I'm going to put a hole. And if you graph this on your calculator, or if you look at our simplified version, the simplified version of the function was x minus 2. That's what my graph is going to look like. It's just a linear function with a slope of 1 and a y-intercept of negative 2. So it's going to look something like that. But when you draw your graph, you need to be sure that there's a hole and that I can see that the hole is at negative 4. So that I can see that the limit as x approaches negative 2 is actually equal to negative 4. Now the last way I want you to show me this limit is numerically. Numerically is when we make the table of values. And I want values that are approaching negative 2. So that means I want negative 1.999, negative 1.99, and negative 1.9. And then on the other side of 2, negative 2.001, negative 2.01, negative 2.1. And here you have to use your calculator to figure these out. Of course, we're undefined at negative 2. And if you plug in negative 1.9 into the function, it's going to give you the value negative 3.900. If I plug in negative 1.99, I get negative 3.990. And if I plug in negative 1.999, I'm going to get negative 3.999. And then on the other side, if I plug in negative 2.1, I'm going to get negative 4.100. If I plug in negative 2.01, I'm going to get negative 4.010. And finally, if I plug in negative 2.001, I'm going to get negative 4.001. And so you can see numerically here that these numbers on both sides are approaching negative 4. And so therefore the limit as x approaches negative 2 of this function is equal to negative 4. So that's algebraically, graphically, and numerically. Notice that they all have the same answer. They all get the same limit because it's all about the same function. All right, let's look at our final question. First part of this question, we've got this piecewise function, and it says given that a equals 1 and b equals 2, evaluate the left and right hand limits as x approaches 2. Does the limit exist? Justify your answer. So let's start. Limit as x approaches 2 from the left of this function is equal to. Now here I need to make a choice. I've got two pieces. If I look up here, if I'm approaching 2 from the left, that means I'm approaching where x is less than 2. And so I need to plug in 2 into my first piece here. Now when you do this on the test, I'd like you to show this step right here where you're plugging in so that I know you're using the first piece. And let's see, 2 squared minus 2, that's equal to 2. Now I need to do the limit as x approaches 2 from the right of f of x, which means I'm looking at values of x that are greater than 2, and that of course is for the second piece. So I'm going to plug 2 in there, and also I'm going to plug in these values for a and b. So a is 1 and x is 2, plus b, which is 2. And if I evaluate that, I get 6. So my limit from the left is 2, the limit from the right is 6, and so therefore the limit as x approaches 2 of f of x does not exist. And it says we need to justify our answer, so I'm going to write because, and the reason that we know that it does not exist is because the limit from the left does not equal the limit from the right. Or you could say the left hand, like you could write out in words, the left hand limit and the right handed limit are not the same. The one-sided limits are not the same. But you need to give some reason, some form of that reason for why the limit doesn't exist. All right, last part. Describe all values of a and b for which f of x is a continuous function. Justify your answers. So if a is 2 and b is 1, as in the previous part, we obviously don't have a continuous function because we don't have a limit at 2. So what this is wanting us to do is to find values, or at least an expression to represent the values that would make it continuous. Anytime you have a piecewise function and you want it to be continuous, we want those two pieces to be equal to each other at the value where we're switching from one piece to the other. We don't want them always equal. We just want these pieces equal when x is equal to 2. So I'm going to plug in 2 to my first piece, and I'm going to set that equal to, and then I'm going to plug in 2 to the second piece. And if I simplify that, I get 2 is equal to 4a plus b. Now this is a little awkward because we've got two variables here, but I only have one equation. I can't actually find values for a and b because there's a lot of values that I could plug in here that would make this equation true. And so this is going to be my answer. If 2 is equal to 4a plus b, if I have any combination of a and b that makes that equation true, then f of x is continuous, which is what we wanted to prove, or what we wanted to make true. F of x is continuous because anytime we are proving continuity, we need to include three things. Because the limit as x approaches 2 from the left would be equal to 2, which would be equal to 4a plus b, which would equal the limit from the right. Oh wait, not 2. I mean not a. I meant for that to be 2 from the right. So we need the limit to exist, which means the left and the right-hand limits need to be the same. And they would be the same because we set it up that way. We set it up for the two pieces to be equal. In this scenario, the value of the function at 2, well, if I'm trying to find the value of the function, I need to look where x is equal to 2. That happens here on this piece because that includes the equal to. And so f of 2 would be equal to 2 squared minus 2, or 2. And so that means that the limit as x approaches 2, wow, there's a lot of 2's in this question. The limit as x approaches 2 is equal to the value of the function at 2. Because the limit would have to be 2 and the value of the function is 2. And therefore they're equal to each other, and therefore the function would be continuous.